Hello guys, let's talk about vapor pressure. So we already know that at any temperature, some liquid molecules are going to have enough energy to escape the surface of the liquid and become a gas. So I have this nice container right here with my water molecules. And some of these molecules, especially on the surface, are going to have enough energy to go to the gas phase, right? And then I'm going to have gas molecules right there. And the pressure exerted by these gas molecules right here in equilibrium with the liquid in this closed container is going to be called the vapor pressure. Of course, there is an equilibrium, so at any point of time, there will be gas molecules that are returning back into the liquid phase. Now, what happens when I have a solution? So let's say that I have water in this container and I have a salt solution. Okay, so let's add some table salt to it or sodium chloride. I'm going to end up having Na plus and Cl minus ions dispersed within these water molecules, right? And there will be an interaction between these ions and the water molecules. So, because of this interaction, the solvent molecules are going to have a harder time escaping to the vapor phase. And even if you just look at this picture, you can see that some of the surface of the water is actually covered with these non-volatile solute particles. So we are going to have less of these molecules from the liquid going into the gas phase. So due to this, the vapor pressure of the solution is going to be lower than the vapor pressure of the solvent if I have a pure solvent. So if you look at this picture here, I'm going to have more molecules in the gas phase compared to this picture right here. Obviously here also we are going to have an equilibrium. Okay, I hope this makes sense. Let's take a look at how to calculate the vapor pressure of a solution. This is described by Rault's law, which tells us that the vapor pressure of the solvent above the solution is going to equal to the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent. Okay, so let's take a look at an example. What is the vapor pressure of the solution prepared by dissolving 0.15 mole of non-volatile naphthalene in 0.85 moles of ethanol? The vapor pressure of pure ethanol at 25 degrees Celsius is 44 torrs. So first we need to identify what is given. We have the vapor pressure of the pure ethanol, right? So this is already given. And we actually have the moles of the solute and the solvent. So from here, we can calculate the mole fraction of the solvent, which is going to equal to the moles of the component, so the moles of the ethanol in this case, which is 0.85 moles divided by the total moles of all components. So 0.85 plus 0.15 moles. Okay, so if you do this calculation, you are going to get 0.85. What is the unit? Unitless, right? Because this is the fraction. So from here, we can calculate the vapor pressure of the solution. Solution right here. Okay, so 0.85 multiplied by 44 torrs. And if you do this calculation, you are going to get 37 torrs, which is indeed lower than the vapor pressure of the pure solvent, which is 44 torrs. Okay, I hope this makes sense. Let's do another example. So here we have to calculate the vapor pressure of the solution prepared by dissolving 200 grams of glucose in 800 milliliters of water. We know that the vapor pressure of the pure water is going to be 24 millimeters of mercury at 25 degrees Celsius, and we have to assume that the density of water is 1 grams per milliliter. So the first thing that we need to do, since we know the vapor pressure of the pure solvent, right, which is 24 millimeters of mercury, we have to figure out what is the mole fraction of the solvent, or water in this case. So we need the moles of water and also the total moles. So let's start with figuring out how many moles of glucose did we have. So because we have 200 grams, so glucose is C6H12O6, right? We can convert it into moles by using the molar mass, which is actually also given here. Grams are going to be on the bottom, moles are on top. So 180.16 grams is 1 mole. Grams will cancel out. We are going to end up with the final unit of moles. And if you do this calculation, you are going to get 1.1 mole. And we are going to do the same for water. So we have 800.0 milliliters of H2O. Now, because these are milliliters, we first have to convert into grams, but thankfully we have the density of water. So now I'm going to use a fraction where the milliliters are on the bottom, the grams are on top, and it's going to be 1 gram in 1 milliliter. And then, because the milliliters canceled out, now I can use the molar mass to convert into moles. We know that 1 mole of water is actually 18.01 grams. So if you do this calculation, you are going to get 44.4 moles of water. All right, so now let's calculate the mole fraction of water, H2O. So we know that we have 44.4 moles on top, and that is divided by 44.4 plus 1.1 mole. These are the total moles, right? The 1.1 is coming from here. So here, if you do this calculation, you are going to get 0.98. The moles cancel out. This is a fraction, no units. And then we can calculate the vapor pressure of the solution. By using the mole fraction, 0.98 multiplied by 24.0 millimeters of mercury. And if you do this calculation, you are going to get 23.52 millimeters of mercury. Okay, I hope this makes sense. See you in the next video.